So, good morning, everybody. Welcome to the latest edition of the Pangolin Seminar. Today, Barbara Schapira from the Université de Rennes will be talking to us about the amenability of colors through critical exponents. So, over to you, Barbara.
Okay, so first I thank you very much for this invitation. Maybe a few of you already listened to talk, so it will be the same that I gave in the past. I said that I would be happy to see faces of participants, but also I will be really happy if you ask questions. It's very useful to me. So please don't hesitate, even all these, what we call in France, stupid questions, which are very useful for the speaker. Okay, so I would like to speak about the result that we obtained with colleagues, Rémi Coulon from Rennes, Rhiannon Dougal, who is now postdoc in England, and Samuel Tapi from Nantes. The result deals with amenability of covers and critical exponents. So of course I will try to define every word that I pronounce, but please tell me if I forget something. Okay. I'm interested in manifolds with negative curvature. So the typical manifold with negative curvature is a n-dimensional hyperbolic space. So if you are not familiar with many other examples, then restrict yourself to the hyperbolic space, the classical hyperbolic space. But if you are also familiar with, you can consider Gromov hyperbolic spaces. I will not define it. And I'm interested in geometry and dynamics of such manifolds, and therefore I will consider a discrete group gamma, which acts properly on X, and usually when I consider such a discrete group, I'm interested in the quotient of the space X by the group gamma, and I'm interested in dynamics of some flows on this quotient, but I will not speak about it now. I'm interested today in geometric questions related to the geometry of this quotient. And these questions deal with a notion which is called the critical exponent. So what is the critical exponent? The critical exponent measures somehow the growth of the action of the group gamma on the space X. More precisely, you choose a point, let's say O, as an origin, and you look at you consider the ball of radius r, and you will count the number of points of the orbit of gamma. So this point is an image of O by some element gamma inside the ball of radius r. So you can count the number of gamma such that the point gamma O is inside the ball of radius r. And this number will grow, of course, and for typical interesting discrete groups, this quantity will grow exponentially fast, and so it's natural to consider the exponential growth rate of this counting function. This is called the critical exponent of this action. And okay, I will not do a lecture on critical exponents, but let me just tell you that for many reasons, it's a good invariant. If you are interested in geometric measure theory, for example, then okay, you have your orbit of your discrete group gamma, which, okay, as it's discrete, it has no accumulation points inside the hyperbolic space, X. But then it will have accumulation points in the boundary. And then, okay, this set of accumulation point is called the limit set. And it turns out, it's a theorem, that this critical exponent is also the dimension, the Hausdorff dimension of this limit set. Not, in fact, it's not completely true, it's almost true. And it's a theorem of Bishop and Jones. If you are interested in more dynamical quantities, you can look at the quotient manifold X over gamma. I recall that if you are not familiar with a general hyperbolic space, consider X as the hyperbolic n space. You look at the quotient X over gamma, you look at its unit tangent bundle, and then you have one of the most classical hyperbolic dynamical system, which is the geodesic flow. And okay, it's a typical geometric example of a hyperbolic flow and another flow more precisely. And if you want to study its dynamics, it's natural to look at an invariant which is called the topological entropy, and this topological entropy coincides with the critical exponent. It's also a theorem, and it's due to Utal and Penny. Okay, so that was just to a kind of motivation to say that the critical exponent is a natural and important invariant of such actions of discrete groups on hyperbolic spaces. But I will not use these notions of dimension and entropy, so I don't define them. Okay, so let me come back to this definition of critical exponent. So it's the exponential growth rate of the number of points of the orbit of gamma inside of ball of radius. Okay, and so of course, if you take a subgroup gamma prime of gamma, the number of points of the orbit of the subgroup inside the ball of radius r will be smaller. That's a kind of obvious remark. So if you have a subgroup, the critical exponent of the subgroup is smaller than the critical exponent of the group. And then, as you are a mathematician, you have this kind of automatic question. But when do we have equality? Okay. And that is the question we will deal with. So what kind of conditions can guarantee that you have equality? Okay. And our result is the following. If you have a discrete group acting on a proper hyperbolic space, think to the hyperbolic n space if you don't want to define hyperbolic spaces, with a certain assumption that I will define later, entropy gap at infinity, and consider a subgroup gamma prime, then they have the same critical exponent if and only if the quotient gamma over gamma prime is amenable. I will define amenability in a second, and I will define entropy gap a little bit later. But okay, let me just say that this is satisfied in many cases. And for example, for those who know for example, if gamma is co-compact, that means that the quotient of X over gamma is compact, or a little bit more general, when gamma is convex co-compact, which is, okay, I will not define it. But these examples are classical, but what I could emphasize if I had one more hour would be that there are many, many other examples.
Barbara,
yes.
I have a question. The subgroup gamma prime, is it normal? Because you take the quotient and you say it's amenable, so that means it's a group.
Good question. If you wait a second, I will define what can be amenability for.
But it's not necessarily a group.
Again?
So is gamma prime a normal subgroup, or?
I understood the question. Please, can you just wait a few seconds?
Okay.
Maybe a few minutes. I will come back to it. It's not necessarily normal. And so it requires a definition of amenability for non-normal subgroups, but this definition exists. So just be patient a few minutes. Okay, this result, let me, okay, I will not do a full story of about this question, but it was already known in many particular cases. Okay, maybe among the first group of results come back to the 80s, two groups of results. On the one hand, Brooks using a classical relation between critical exponent and eigenvalues of the Laplacian obtained this result for convex compact actions on the hyperbolic space, but with some restriction that the critical exponent should be large enough, which is a technical restriction due to this approach with Laplacian. On the other hand, Grigorchuk and Cohen in the 80s also, completely independently and with completely different proof, obtained the same result, but for a free group acting on its Cayley graph. And it was a kind of very impressive technical proof, but very specific to this case. And then, I forgot the date, but Manuel is here, so maybe he can tell us, maybe in 2010, okay, maybe less than 10 years ago, I would say, or Manuel Stadelbauer obtained this kind of result for convex compact actions and in some case geometrically finite actions on the hyperbolic space through coding arguments.
Manuel says that was in 2013.
2013. Okay, thank you. A little bit later, Rhiannon Dougal and Richard Schacht applied Manuel's results to get a similar result for convex compact actions in variable negative curvature, so a little bit more general than the hyperbolic space, but with similar algorithms. Then in a few years later, or maybe at the same period, Rémi Coulon and Françoise Dalbeau and Andrea Sambuzetti obtained it for co-compact actions on cat-1 spaces, so more general than manifolds. There are no more manifolds. And in 2003, Thomas Roblin proved one direction in a very general context. He proved that amenability implies equality, but he didn't need the entropy gap, but he needed to consider normal subgroups. Okay.
May I ask a question, Barbara? Yes. So you say your theorem is for hyperbolic space. So your theorem does not yet apply to general Hadamard manifolds. Is that right?
It is. It's okay. So the typical example, the first example is a hyperbolic space. Right. The second example is Hadamard manifold.
Okay.
Variable negative curvature.
So by hyperbolic space, you mean Hadamard manifold?
No, okay. Let me.
It's in the sense of Gromov, no?
Yes.
So
the typical example is the constant curvature hyperbolic space. The second typical example is a Hadamard manifold, so manifold with negative curvature.
Right, right.
And the third typical example is when X, okay, if I increase the generality, then you will have the cat-1 spaces, which are a little bit less regular, and then the most general is when X is Gromov hyperbolic.
Right, okay.
And these are, okay, Gromov hyperbolic space is a generalization of negative curvature to metric spaces. Mm-hmm. So there are no more manifolds.
Right, okay.
So our result applies to all these kind of spaces, not completely general hyperbolic spaces, because Gromov hyperbolic spaces can be very strange, and we need that they are proper. So closed balls should be compact. But of course, it includes Hadamard manifolds. Hadamard manifold, I have a doubt if it's non-positive or negative curvature, but for us, it's negative curvature. Is it? Does it answer the question?
Yes, sorry, I was thinking in terms of manifolds. I'd completely forgotten about Gromov and so on.
Yes, it's a okay. So it applies in all cases, but except for technicalities that I will not develop today, the arguments are essentially the same. So you can really think to the hyperbolic space or Hadamard manifold. Okay, these Gromov hyperbolic spaces they lead to some technical problems, but not to a change of strategy. So I will not speak about that. Okay. So I still have to define what is amenability. Okay. Maybe before a definition. Okay, as was said before, usually amenability is a notion which is defined for groups. So if gamma prime is a normal subgroup of gamma, then of course gamma over gamma prime is a group which can be amenable or not. That's the definition of amenable group is quite classical. And the typical amenable groups are, for example, Z or ZD, and the typical non-amenable groups are, for example, the free groups. But there are, if you are familiar with amenability, there are many different characterization or definitions of amenability, and we will, in our proof, the one which is relevant is the following one, which works perfectly for non-normal subgroups. So we will say that the group gamma prime, so gamma prime is a subgroup of gamma. Gamma prime is co-amenable in gamma if, when you consider the regular representation, so it's a representation rho from gamma to the unitary operators on L2 of gamma prime, which is defined by composition by gamma. So if you take an element of L2, rho of gamma applied to this element phi is just phi composed with gamma. Maybe there is a -1 here, but I never remember if you have to put it or not, but it's not important. So this representation, okay. I come back to the beginning of my sentence. So the group gamma prime is co-amenable in gamma if this regular representation almost admits invariant vectors. What does it mean? It means that for all epsilon positive and for all finite sets S in gamma, there exists an element phi in L2 such that which is almost invariant in the sense that for all elements gamma in S, rho of gamma does not move phi too much. In the classical definition of, in one of the maybe more classical definitions of amenability, one speaks about Fellner sequences, and then you have to think about phi as the indicator function of a set whose boundary is not too big when you translate it by gamma. Okay, I don't want to develop too much. Maybe if you know amenability, this definition shows you that it extends without problem to the case of non-normal subgroups. And if you don't know amenability, I would say that it's preferable to keep in mind the typical amenable and non-amenable groups, which are ZD on the one hand and the free groups Fn on the other hand. Okay. And then we want to speak about amenable or non-amenable covers. So I just drew pictures. If you consider, let's say, a surface S, which is the quotient of the hyperbolic space H2 by a certain group gamma. And then you can consider a cover S prime, which is the quotient of H2 by gamma prime. And on my picture here, if gamma prime is a subgroup of gamma, here on my picture, it's a normal subgroup with gamma mod gamma prime, which is isomorphic to Z, then you obtain a Z cover. And a Z cover is a typical amenable cover. And then it means that, okay, you have your surface S here, and the cover is just infinitely many copies of S, which are glued along the calligraph of Z, as in the picture. And then you could try to draw F2 cover, F2 being the free group of a compact hyperbolic surface. And so for I tried, but as you know, F2 is a very large group, and you can try to, with hyperbolic surfaces, you can try to play, I should add a picture. You consider a compact hyperbolic surface, for example, like that, and then you cut it along, let's say, two curves. And then you have an elementary piece, which is like that. Where the orange boundary is here and the pink boundary is here. And with these elementary block, you can build many covers of these compact hyperbolic surfaces. For example, this one, you can imagine that the pink curve is here and the orange curve is here. Okay. I'm not sure that what I'm doing is clear. Ask questions if it's not clear. And I can build more complicated covers, like an F2 cover here. Okay, of course, I will not draw every curve, but and okay, so that was just an attempt to show you that there are a lot of amenable covers on the one hand and of non-amenable covers on the other hand of a compact hyperbolic surface. Okay, and so let us come back to the statement. We said that okay, the critical exponent of the subgroup gamma prime is equal to the critical exponent of the group gamma if and only if the quotient gamma over gamma prime is amenable. So if I come back to the examples, it means, okay, the critical exponent, I prefer the dynamical point of view. The critical exponent is the entropy of the geodesic flow on the quotient. So delta gamma is the critical exponent delta gamma is a dynamical invariant of the surface, and delta gamma prime is a same invariant but for the covering surface. And what the result says is that these two invariants are the same if and only if the covering group is amenable. Okay. So one thing that I didn't define in the statement is this notion of entropy gap at infinity. I will not develop too much, but we'll give a definition. Okay, so the definition with picture would be better. So the group gamma acts on the X. We said that. For example, X is a hyperbolic space. And we are interested in the growth of an orbit. So I take an origin O and I will look at the orbit gamma. Okay, but then I will be interested in, okay. I choose a compact set, let's say K, containing the point O, and I look at these images. And if you imagine the quotient surface, so here you are on X, which is a hyperbolic space, for example. But if you do the quotient by gamma, you have the quotient space X over gamma, which is maybe not a compact space, you don't know. Maybe it's compact, maybe not. And the point is that each segment, geodesic segment from a point O to a point gamma O, if you look at its image on the quotient, it gives a loop starting from the image of O, let's say O bar, and coming back to O bar. Okay, so all of these segments induce loops like that. Okay, and what we will do is we will, it's a kind of dynamical notion. You consider this given compact set, for example, here, it's a compact set on the quotient, and you will be interested in the loops which are representing excursions outside a compact set. So it means you are interested in loops which start from this green compact set, leave it, and come back. And you are not interested in more complicated loops which can maybe stay a long time in K, leave, come back, leave, come back, leave, come back. These ones do not represent excursion. What is an excursion? An excursion is a loop which starts from the compact K or K bar, leaves the compact set, does something outside, and come back once. And that is what is encoded here. We are interested in the set of element gamma, such that when you look at the segment from O to gamma O, it intersects the orbit of the compact set K only at the beginning and at the end. So this element here will give the set an element of gamma K, but I should for another one. For example, here you will have an element, maybe GO, where G is not an element of gamma K because the loop from the segment from O to GO, it goes outside K, comes back to a copy of K, and leaves again and come back. So on the quotient, it will induce a loop which goes outside K, come back, outside, come back. Okay. So this one is not good, not in gamma K, and this one is in gamma K. Okay. So this set encodes excursions outside K.
Just to make sure of something, so the segment joining the 2 points, 0 and gamma 0, is not necessarily unique, right? But you don't really care about which one you take.
Okay. If you are in negative curvature, on manifolds of negative curvature or cat -1 spaces, it's unique. And if you are on Gromov hyperbolic spaces, it's not necessarily unique. And then you have to be careful with the definition, but it's just a matter of technicality. It's not you have to choose a definition. There are several choices which will not be equivalent, but not be exactly equivalent. But it's just a matter of technicality. It's not a. It's just a technical problem, but it's not a true problem. It's not maybe not a very good answer, but is it okay? Or?
Yeah, it's okay. So, merci.
Okay.
Excuse me, Barbara. Silly
Yes.
question again. Can you just remind me of the statement of the theorem, whether the theorem applies to groups which admit an entropy gap or which don't admit an entropy gap?
Which admit.
Okay, it applies to groups which admit an entropy gap. Okay, great.
The theorem is here.
Okay, with
We
entropy
assume
gap.
that there is an entropy gap, but I still did not define it. So let me define it.
Okay.
So we have this subset. This gamma k is a subset of gamma. In fact, it's not a subgroup. It's a subset which measures excursions. And for people who are used to dynamics, you should think to statements as a lemma in ergodic theory. So it really measures the excursions outside the compact set. Okay, it's a subset, but when you come back to the definition of critical exponent, you can define the exponent of a subset. It's just the growth rate of a subset of an orbit, and it's perfectly defined. And then, of course, it depends on the choice of the compact set. And then you consider the infimum over all compact sets of X of these exponents. All these exponents are less than the critical exponent of gamma. Therefore, the infimum also, and the infimum can be strictly less or not. Okay. And the typical example where you have maybe the definition is of entropy gap is you have an entropy gap when the entropy at infinity is strictly less than the critical exponent. The critical exponent at infinity is strictly less than the critical exponent. And the typical example is when x over gamma is compact. For convex co-compact, then gamma k will be finite, and then the critical exponent, you will have an entropy. Okay, this notion is in fact is a geometric version of some notions which were already studied in symbolic dynamics or also in the context of random walks. And so we use terminology coming from dynamical system, symbolic dynamical system, and we call these actions strongly positively recurrent actions. It turns out that other people in geometric group theory used the same notion maybe 1 or 2 years before us, and the terminology was a little bit different. Was on the one hand Rose-type actions, and also statistically convex co-compact. Statistically convex co-compact. It's a shame, but a gap in my mind. I don't remember people who did that. Okay, it's bad, but it's like that. I forgot the reference. Okay, so it turns out that this notion is very natural in different contexts. And okay, that is the assumption, but maybe if I have a few minutes at the end, which is not likely, but anyway, maybe I will come back to it. But okay, we assume this entropy gap, and of course, it is satisfied for convex co-compact action. It is satisfied for the action of a free group on its Scaly graph. It is satisfied on the examples of Manuel Stadelbauer. Here also, of course, on co-compact actions. So on all cases where the theorem was known, this entropy gap is satisfied, and this assumption is more general quite more general than the preceding ones. Okay. Okay, so the typical example without entropy gap are the infinite covers of compact surfaces. Why? Because entropy gaps measures the complexity of the dynamics outside a given compact set K. That if you have an infinite cover of a given surface, you have the same complexity outside the compact set than inside. You have the complement of this compact set is not less complicated than the compact set. So you cannot have entropy gap. It's not a proof, but it's the heuristic of the proof. So there is no entropy gap when you consider an infinite cover. And then, okay, there are many examples with entropy gap. So as I said, there are the compact or convex. When you look at gamma, when gamma is a, sorry, my sentence does not want to go out. When gamma is when x over gamma is compact or convex or compact, that's the first typical example, but it's not very interesting because the theorem was already known in this case. There are several other families. One of the nicest families that I like, we called it Ancona surfaces, because there was an old unpublished paper of Alano Ancona with some examples in this family. The point is okay, you start with an infinite cover of a compact surface, and you will pinch some curves to have a surface which look like an infinite cover of compact hyperbolic surface, except that at some place you have this part of the surface which almost looks like a finite volume hyperbolic surface. And okay, it would be a specific talk to develop that, but this kind of example will have an entropy gap. And it provides many examples which are not convex co-compact, not geometrically finite, and which have entropy gaps. So there are a lot of new examples to which our result applies.
And in your Ancona surface, you have many ends of the surface which are approximated by this kind of.
Again.
In your Ancona surface, you will have a lot of ends of the surfaces accumulated by this, or they are in a compact part of the surface. It's like a.
I'm not sure to understand.
I just want.
If you are familiar with geometrically finite manifold, what is for those who know, what is a geometrically finite manifold? Let's say hyperbolic manifold. It's a manifold which can be decomposed into a compact part, okay, and finitely many ends, which are either cusps or funnels. My picture is quite simple. And okay, so a geometrically finite hyperbolic manifold or negatively curved manifold is a manifold which admits a compact part and finitely many ends whose geometry is very simple. And as the geometry is very simple, we understand the dynamics, and the dynamic is very simple and has lower complexity than the full dynamics. And so all the theorems in dynamics over geometrically finite manifolds use this kind of arguments that, okay, you know the geometry of the ends, and therefore you know the dynamics of the ends. And the point is that entropy gap allows to say that, okay, you have a compact set, and outside the compact set you have things but you have no idea about these things. Okay. You don't know anything about the topology or the geometry of the ends. Just the only thing that you know is that from a dynamical point of view, the complexity of these ends is lower, strictly lower than the complexity of the full many. That is the dynamical way of thinking. Okay, so maybe I will not develop because time is going too fast as usual. But okay, in some sense, our result is relatively optimal in the sense that okay, there are trivial counterexamples without hyperbolicity. There are trivial counterexamples without critical gap, entropy gap. The only thing that we could improve is that in higher rank symmetric spaces, one direction is proved. It's a recent result of Olivier Glorieux and Samuel Tapit. And okay, it would be of course interesting to prove the converse. But okay, I would like now to come to okay, if you have no more question on the statement, maybe I will come back to the statement once again. I would like to spend the rest of the time to present the ideas of the proof.
Actually, I have a question on your statement.
Yes.
You know, when I think about all your definitions, you don't really need gamma prime to be a subgroup. Could it be true for any, you know, for any subset of
gamma? Okay, if gamma prime is not a subgroup, you lose geometric intuition. But okay, this is defined. So this is defined, and let me. I should check if the notion of co-amenability seems to work also, and maybe it works also. I never thought to this question because if gamma prime is not a subgroup, but just a subset, you don't have this intuition of covers. But maybe you're right. I don't know. Maybe it's an exercise, follow the proof and see if.
Well, I mean, it's true. I mean, we you know, we mostly care about subgroups, but yeah.
There's an example by Matsuzaki and Falk. What they did is they just considered a surface which has a decomposition into somehow uniform bands. And they only looked at the graph associated to this decomposition. So you don't have to have a covering subgroup at all. And there is a similar result, if I remember correctly. But I don't remember precisely the result.
I would be interested in
the
proof. Okay.
So
anyway, so, okay. I would like to present the ideas of the proof because I think maybe the ideas of the proof are as interesting or more interesting than the result, even if the result, if I like the result a lot, but the proof is really okay. It's really satisfactory. So I would like to explain it a little bit. Before explaining the proof, I need to recall or present a tool which is classical in the subject and which is very important in our proof. So you have a hyperbolic space X and you have a discrete group acting on it, and so you have this orbit of gamma which accumulates on the boundary, and it comes back to Sullivan that okay, and Patterson and Sullivan that you can consider this Poincaré series, which is the sum of a gamma of the exponential of minus s times the distance from O to gamma O. And this series has a critical exponent, which is exactly delta gamma. That's a very elementary exercise. it means that for S larger than delta gamma, this is finite, and for S strictly smaller, this is infinite. Okay, that's a simple exercise. And okay, then the Patterson-Sullivan construction will give you a measure on the boundary, on the setup of accumulation point of your orbit, which is somehow the most geometric measure that you can hope on your limit set. Out of measure, you can think to it as a Lebesgue measure on the limit set. How they do that? For S larger than delta gamma, so this series is finite, and you consider an orbital measure, which you put a Dirac mass on every point of the orbit, and you weight it by this exponential, and you divide by the total mass of this measure, and so you get a measure on US, which is a sum of Dirac masses. Okay. And now you let S decrease to delta gamma, and it's a classical fact of measure theory that all these new S are probability measures on X union the boundary, which is a compact set. And a sequence of probability measure on a compact set has always accumulation point, weak limits. So take one weak limit of this new S, and you get a measure nu, which is supported a priori on X union the boundary. But okay, that's I will not give all the details of the construction, but it's easy to show that it will be supported on the boundary and will be not invariant exactly, but quasi-invariant under gamma. So it means that if you push the measure by any gamma on the group, you get a measure which is equivalent to, and you have explicit formulas which are very useful in the proofs, but not in the talk. So it's really an explicit relation. And the point is that for those who like dynamics, for example, me, if you consider the unit tangent bundle of the space X, that's the only advantage of electronic talks is to use this kind of color tools. So you have your set, you have parabolic space, and a unit vector V can be if you have a unit tangent vector, it determines a unit geodesic on the hyperbolic space. This unit geodesic has two endpoints in the boundary, V minus and V plus, and you get nice coordinates of your vector V. You associate to be V minus, V plus, and a real parameter. So it's called the Hopf coordinate. So the unit tangent bundle is homeomorphic to the boundary times R. This is called the Hopf coordinate. It comes back to the 30s. It's due to Hopf to use this point of view. And on this unit tangent bundle of your hyperbolic space, you can build a measure which is essentially nu times dt. And okay, there is a density that I will not. I will just hide it. And this gamma invariant. Okay, you can make it gamma invariant, and so it gives you a measure on the unit tangent bundle of the quotient manifold. And on this measure on the unit tangent bundle of the quotient manifold is an invariant measure under the geodesic rule because of the dt here. And this measure is the nicest measure that you can dream when you like dynamics. It's ergodic, it's mixing, it's a measure of maximal entropy. It has all the possible qualities of an ergodic measure in ergodic theory. And it's called the Bowen-Margulis measure. So this construction is very important, and our proof relies on a variant of this construction. A strange variant, but still a variant. Okay, and so let me go to the proof. So the strategy of the proof is the following. So recall maybe what is amenability first. amenability is here. A subgroup gamma prime is co-amenable in gamma. It's a regular representation from gamma to the unit operator on L2 of gamma, but gamma prime almost admits invariant vectors. So, and let me recall what I want to prove. I want to prove that critical equality of critical exponents is equivalent to amenability of gamma mod gamma prime. Okay. In fact, Roblan proved this direction, and I will not develop this direction. This was known since a long time, so I will just present you the strategy of the converse direction. So if the critical exponents are equal, then can you prove that you have co-amenability of gamma prime in gamma? So I consider the regular representation of gamma inside the unit operator on L2 of gamma with gamma prime, and I would like to find almost invariant vectors for this representation. That's my goal. Okay, so first I will consider a twisted Poincare series. So sum over gamma, the exponential of minus s distance from O to gamma O times rho of gamma. So rho of gamma is a unit operator on L2. L2 will be, it's a Hilbert space that will be called H in the. Okay, this sum, the first step is to show that, okay, this sum can have a meaning, has a critical exponent, and this critical exponent, delta rho, is inside the interval delta gamma prime, delta gamma. And for S larger than the critical exponent, this sum A of S is well defined as a bounded operator on H, on the Hilbert space. If you can do that, at the second step, you want to mimic the Patterson-Sullivan construction and build a twisted Patterson-Sullivan merger, A rho. So you don't have to worry at this time, but okay. What you will do is to construct a sum over gamma of exponential minus s distance from O to gamma O, rho of gamma, times the Dirac mass at gamma O. So it means that you have a measure on X union the boundary, which is whose values are bounded operators. That's a kind of strange object, but you have just to use it slowly, and the second step will consist to prove that what we do has a meaning.
So, sorry, what is d gamma O? The last term in this formula? I forgot.
It's always the same thing, that you have a point O and you look at the orbit of the group. So gamma O is a point of the orbit, and so that's a Dirac mass.
Ah, okay.
And so it's a kind of, it's this object will eat Borel set on X in the boundary, and give you the measure of a set is a bounded operator. Okay, maybe if it has a meaning, if you are lucky. But that's the step 2, is to prove that it has a meaning. The step 3 is the following: when at some point you have to use the assumption, when the critical exponent delta rho is equal to delta gamma, which is implied by the fact that delta gamma prime is equal to delta gamma. And when you have this entropy gap, then you can prove that this A rho is absolutely continuous with respect to the classical Patterson-Sullivan measure. What does mean absolute continuity? Then come back to the basic definitions in ergodic theory. It means, or in measure theory, it means that if you have a set such that the measure nu of A is 0, then A rho of A is 0 as a bounded operator. Nu of A is 0 as a number, and A rho of A is 0 as a bounded operator. So it is, it has a meaning, and it is true. to get absolute continuity. And then, okay, you have absolute continuity, and then you will use an ergodicity argument to get that if you have a measure a rho which is absolutely continuous to mu, it means that you have a Radon-Nikodym derivative from a rho with respect to nu, which is a priori a function with values in the set of bounded operators. And by ergodicity, this function will be constant. But this constant will be a bounded operator. Because, okay, this one is a classical measure with values which are numbers, positive numbers, and this one is a measure whose values are bounded operators. Okay, so the constant is a bounded operator. And now the final step is a kind of abstract nonsense. I mean, it's a formal thing that, okay, by construction of a rho and nu, you have almost quasi-invariance relation under gamma. And so a rho is quasi-invariant under the group, nu is quasi-invariant under the group, and it will force your constant, multiplicative constant to be essentially constant, and this will produce the almost invariant vectors that we were looking for. So that's the general strategy of the proof. And now I don't know when I began, and if I have a few more minutes.
According to my clock, you have 5 minutes. Okay.
Okay. So if I have 5 more minutes, I can give some more details on some of these steps, if you want. So the step 1, I want to define a twisted Poincaré series, twisted by a representation. So first I write it, and then I want to give it to it a meaning. So the point is that the Hilbert space L2 of gamma mod gamma prime, it's a set of functions with real values, and so it has a partial order coming from the fact that it's a set of functions with real values. And this partial order is compatible with everything that we will do. And that will really be an important technical point. That okay, you will say that an element of H will be positive or non-negative if for all element Y in gamma mod gamma prime, phi of Y is positive. It gives you, it leads to the definition of a positive cone, and which is a subset of H, and then a bounded operator on H will be said positive if it preserves H plus. And the point is that all rho of gamma, by definition of the regular representation, it does not change the positivity of the functions. So these are positive operators. And this will allow to define the critical exponent. So it's an elementary exercise, but this notion of order and positivity allows to show that okay, if I look at the infimum of all S such that the operator A of S is well defined and bounded as an operator on H, this is well defined thanks to these notions of order and positivity. Okay, so I have a critical exponent, and then as a gamma prime is a subgroup of gamma, it's easy also to check, or elementary maybe more than easy. It's elementary exercise to prove that the critical exponent of this twisted series is between delta gamma prime and delta gamma. And the funny point is that the assumption delta gamma prime equal delta gamma is only used to guarantee that delta rho is delta gamma. So in fact, we prove an abstract result on representation rho on Hilbert spaces with a partial order and such that delta rho equal delta gamma. So delta gamma prime does not play another role.
Excuse me, Barbara. Yes. I'm a little bit puzzled. Why do you need the partial order in order to have the convergence of the twisted Poincare series? I mean, it's a Hilbert space, so you have a notion of convergence.
You really have to do the exercise, but if you want to know that for S larger than delta rho, AS will be bounded, and for S smaller than delta rho, it will not.
Ah, okay.
Then you have to, if you want to compare such things.
I see, right, yes.
To compare operators, you need an order.
Ah, right, I get you.
Okay, then step 2 is to build a measure with valued in the set of bounded operator on our Hilbert space. So the step 2 is, okay, you have to play with some objects I'm not so familiar with, but my collaborators are more. You take a non-principal ultrafilter, which is a way to take subsequence in a consistent way. And you build a kind of larger Hilbert space, H omega, and extend rho to this larger Hilbert space on which you still have a partial order. And the advantage is that on this larger Hilbert space, which is a set of all sequences of element of H, the notion of almost invariant vector becomes a notion of invariant vector on this new Hilbert space. So now our goal is to find an invariant vector on this new Hilbert space for this new representation. So it's a technical step. Maybe I will not take time on that. And then you define a kind of, you mimic the Patterson-Sullivan construction. So you define this kind of measure, and you choose a sequence converging to the critical exponent, and you try to make this measure converge. And the point is that usually ultrafilters do not go very well with measures, so you have to be quite careful, but it works. For any fixed function on X union the boundary, you look at the integral of f with respect to this measure, and you take limits thanks to the ultrafilter, and you define a quantity a rho of f, and this defines a linear functional which is positive and which to each map f associate a quantity a rho of f, which is a bounded operator on this strange Hilbert space. So we give a meaning to a kind of Patterson measure on the boundary with values bounded operator on a Hilbert space. And it's not difficult to check that, in fact, it's a non-zero measure on the boundary, and okay, with values which are operators. And if you accept that, okay, you can work with them. And now the step 3 follows the classical argument in the theory of Patterson-Sullivan theory, if you are familiar with, for those who know it. You consider shadows. You have your origin O, and you take a small balls, no, not small balls, balls which are far from the origin, and you look at the shadow of this ball. And when the ball is goes farther and farther, these shadows becomes smaller and smaller. And okay, these shadows are a nice subset of the boundary, and the classical Sullivan shadow lemma tells you that the Patterson measure of a shadow of a point, maybe a new picture would be useful if you have a point O, a point gamma O, and you take a small ball here, and you look at the shadow. This set on the boundary decrease exponentially fast when gamma O goes far from O, and precisely the exponentially fast is described by this delta gamma. And that is a classical proof, which is very okay, maybe not so easy, but classical at least since the 80s. And the point is that for the measure A rho, half of the proof works in the same way. And we get a half shadow lemma, we get just the upper bound. So this is an operator, a bounded operator. So I take the norm, which is a number, a real number, and this norm is less than the exponential of, in fact, it's delta rho times the distance. But as delta rho is equal to delta gamma, I can erase delta rho and it's also delta gamma. Okay. And then, okay, so I have a kind of absolute continuity result. The measure, the norm of the measure of the shadow for the strange measure A rho is smaller than the Patterson measure of a shadow. And the point is that, okay, the only place on the proof, it's used only once. The only but crucial point where we need the entropy gap is to show that, okay, with shadows you can recover all Borel sets of positive measure. So in other words, the point which lie in infinitely many shadows have full measure for both measures nu and A rho. And it's really the only place where it's used. And this allows to go from this easy inequality to a non-trivial statement, which is that A rho is absolutely continuous to nu with respect to nu. In the sense that if a set is of measure 0 for nu, then it's of measure 0 for A rho. And okay, in fact, there is we discovered all the books on measures with values in vector space. And so you have a version of Radon-Nikodym theorem in this context. And you have, therefore, a Radon-Nikodym derivative. So it means that if you integrate a map F, which is a map on X union the boundary, then the integral of F is, with respect to the measure A rho, is, okay, A rho, there is a phi here, but phi is just because A rho is an operator, phi is an element of the Hilbert space. So A rho times applied to phi is a measure which has values in H. It's more comfortable, but it's detailed in the proof. So if you integrate F with respect to this strange measure, it's the same as the integral of F times a Radon-Nikodym derivative times the measure of the nu. And this Radon-Nikodym derivative is a map, a bounded map from your hyperbolic space union the boundary with going to the Hilbert space H. And
excuse me, Barbara, sorry to interrupt. Can you start wrapping it up now, please?
I don't hear you, but I guess that I have to conclude.
Yes, that's right.
And so I conclude here. Then you have an ergodicity argument, which allows to say that this Radon-Nikodym derivative has to be constant, and this constant okay, the final step is a conclusion which is just a formal thing, which is that this constant has to be invariant by construction, and it is a desired almost invariant or invariant. And so the proof finished like that. And so I'm sorry that I was over time.
Thank you very much, Barbara. So everybody please unmute your speakers so that we can thank the speaker. That's a really nice proof. That's a really
It's very nice. Yeah.
Yeah.
It's impressive.
It's I love the way you take the classical what's it called, Patterson-Sullivan series and twist it. That's lovely. Anyway, let's ask questions. Does anybody have any questions for Barbara, please?
You have some case where you can have a full shadow lemma in your twisted context. Some hypothesis that helps you to fix the other half of the proof.
Ah, that's a good question. My slides disappeared.
Just share them again. I just stopped your sharing.
Okay. In fact, where is the shadow lemma? The half shadow lemma says you that the norm of an operator is smaller than a number. Okay. Probably in your life you already did a lot of exercises where you could bound from above the norm of an operator, but bound from below, it's hard to think. So for the moment, we have no way. Try to write it, and then we discuss. But yeah, we don't know if it's possible to have a version of the lower one, but it's not clear at all because it's an operator, and as an operator, it could be very small for small functions. It's not clear at all if we can get a lower one. Maybe. But, and anyway, we didn't need it, and we didn't see how to get it. So we let it side point.
Are there any other questions? I guess it would be remiss of me not to ask if if a similar result applies for Anosov representations in higher rank spaces.
I guess it should, but
you understand, I have to ask that on account of
again,
François Laborie.
No, I don't. Can you repeat your sentence?
Sorry, I just said it would be remiss of me not to ask about Anosov representations in higher rank spaces.
So, in fact, in a higher rank symmetric spaces, you have the so-called easy direction showing that if gamma prime is a normal subgroup of gamma, then you have equality of critical exponents. This has been done recently by Olivier Glorieux and Samuel Tatib.
Olivier gave a talk in this seminar about this. Do you remember, Graham?
Yes, of course.
Yes,
I remember.
it was about this.
And in fact, their proof used the same approach than Roblin's arguments. And okay, so this direction works, and as they assume that the subgroup is normal, they don't need to speak about entropy gap and so on. And then if you speak about Anosov representations are somehow the natural generalization of convex co-compact groups in high rank.
Exactly.
And okay, I would like to have a version for entropy gap actions. Okay, there are points which are not developed in higher rank. Ergodic theory does not work so well.
Right.
Some things work, but some of them not.
Right.
So the problem in higher rank is not the formal construction of measures with values in bounded operators. The problem is the ergodic argument.
The problem is what?
The ergodic step. Ergodic
okay.
theory of the ergodic theory. The ergodic part is relies on the ergodic theory of the geodesic flow in negative curvature, and okay, it's a typical example of a Anosov flow which is ergodic and which has a lot of stochastic properties, and the step is not so clear in higher rank.
Understood. Thank you.
But we have hopes that it works at the end.
Right. So this is the next big step, really, is to look at.
But somehow after this work, there was a kind of lockdown
Really?
without school, and
Really?
so it stopped a lot of works.
What on earth could that be about? Right. Well, Are there any other questions?
Yeah, I have a question. Means just to know. So if you have a group, you know, like in your case, like acting on a Gromov hyperbolic space, and you know that the critical exponent is 0. What can you say about the group itself? Can you say something, I don't know, minimal or something? I don't know. Can you say something?
For a discrete group acting on a general hyperbolic space.
Yeah, I mean, that's kind of you. I mean, you're in your assumption, you have this group acting on X on a hyperbolic space. You also have like this, from what I remember, like the gap. So of course it doesn't apply. I mean, so I imagine that the gap implies that the group itself has positive critical exponent.
Yes.
But now, you know, just say you don't have this gap, but you know, because you know that the critical exponent itself is 0. What can you say about? I mean, can you say anything? I don't know. In relation with your result.
Okay, I know the answer for in the hyperbolic, the classical hyperbolic space.
Yeah.
Where,
yeah.
If your group contains a free subgroup, then the critical exponent will be positive. Then, but
it's more in the other direction.
I guess the same is true if you have a discrete. It's the other direction. If the if the critical exponent is positive, is strictly positive, then if the group contains a free subgroup, then the critical exponent is positive. I would say that this should work also for Gromov hyperbolic spaces. And then, so if your exponent is 0, then you know that you
have
contain.
That, yeah.
But saying more, I'm not okay. I'm not an expert in geometry group theory, and then for group acting on, as we are speaking about groups. I didn't say it, but our groups are not necessarily finitely generated, so they are very general, and I'm not sure that one can say general things for all general. Infinitely generated groups. It's a huge world. So I don't know, except that they don't contain free subgroups or free semi-groups. If you I should ask to my collaborator Remy, maybe he knows. I will ask, but I don't know.
So now it's 12:25 here in Rio de Janeiro. So I reckon now is a good time to wrap everything up. So everybody, please unmute your speakers once again and thank Barbara for a wonderful talk.
Thank you very much, Barbara. It was very nice.
Thank you for the invitation.
That was a great talk. I really like that. But before I finish the recording, I just want to do a little bit of advertising for next week's talk. The next edition. So the next edition of the Pangolin Seminar will take place on the 23rd of March. And Louis Merlin from Aachen University will be speaking to us about the relations between the universal type Muller space and anti-de Sitter geometry. I'd also like to do a little bit of advertising already to have that on the video. On the 20th of April will be a very special moment for the Pangolin Seminar. Our little baby pangolin will be 1 year old on the 20th of April. And we will have Jean-Marc Schlenker from the Université de Luxembourg, who will, well, the content of his talk is yet to be announced. So thank you very much, everybody, for coming along. And thank you very much once again, Barbara, for a great talk. I'm going to stop the recording now.